Trillions of quantum particles are flowing through your body, each one existing in a ghostly state of multiple possibilities until something, perhaps your attempt to detect them, forces them to choose a single reality. These particles don't behave like anything in our everyday experience. They can be in multiple places simultaneously, spin in opposite directions at once, and somehow know when they're being watched, instantly snapping from fuzzy probability clouds into definite, measurable states. We thought observation was a passive act of simply looking at what already existed. Quantum mechanics revealed we were completely wrong. What Niels Bohr, Werner Heisenberg, and their colleagues discovered in the early 20th century shattered our most fundamental assumptions about the nature of reality. Before quantum mechanics, we believed that particles had definite properties whether or not anyone was looking. Electrons had specific positions, photons had definite energies, and atoms followed predictable paths through space. The act of observation seemed as innocent as glancing at a distant mountain. Surely looking at something couldn't change its essential nature, but quantum experiments revealed something far stranger than anyone anticipated. When you're not looking, quantum particles exist in what physicists call superposition, simultaneously occupying multiple states, multiple positions, multiple energies at once. An electron orbiting an atom doesn't follow a definite path like a planet or on the sun. Instead, it exists as a probability wave spread throughout space, with different likelihoods of being found in various locations. Only when you perform a measurement does this wave collapse, forcing the electron to appear at one specific location as if it had been there all along. Consider this mind-bending fact. In the famous double-slit experiment, individual photons somehow pass through two separate openings simultaneously, interfering with themselves to create patterns that are impossible if the photons followed definite paths. Yet the moment you place a detector to see which slit each photon actually uses, the interference pattern vanishes completely. The photons begin behaving like ordinary particles, each passing through only one slit or the other. The very act of observation fundamentally changes what's happening at the quantum level. But here's what makes this truly unsettling. The quantum world doesn't just affect exotic laboratory experiments, it is the foundation for every atom in your body, every chemical reaction in your brain, every biological process that keeps you alive. The electrons flowing through the neurons in your brain right now exist in superposition states until biological measurement processes collapse their wave functions. The photons carrying visual information from the screen to your eyes are quantum particles whose behavior depends on how you observe them. You're not just learning about quantum mechanics, you're experiencing it directly through every sensory perception. The implications reach far beyond academic physics. Quantum measurement theory has already revolutionized technology through laser systems, magnetic resonance imaging, atomic clocks, and the emerging field of quantum computing. Engineers at companies like IBM, Google, and D-Wave are building computers that harness superposition and measurement collapse to solve problems impossible for classical machines. Researchers like Anton Zeilinger and Elaine Aspect have demonstrated quantum entanglement effects, where measuring one particle instantly affects another particle across vast distances, as if observation creates mysterious connections that transcend space and time. Tonight, we're going to explore three profound revelations that will forever change how you understand the relationship between consciousness and reality. First, we'll discover that quantum particles exist in multiple contradictory states simultaneously until the moment of observation forces them to choose a single outcome, suggesting that reality itself might be fundamentally uncertain rather than determined. Second, we'll uncover how different types of measurement can reveal completely different aspects of the same quantum system, as if particles somehow know what questions you're asking and adjust their behavior accordingly. Third, we'll reveal how quantum entanglement allows observation of one particle to instantaneously influence another particle anywhere in the universe, challenging our basic assumptions about locality and the speed of light limitations. What you're about to learn goes beyond physics into the fundamental nature of knowledge, consciousness, and reality itself. The quantum measurement problem, why and how observation causes wave function collapse, remains one of the deepest unsolved mysteries in science. Some interpretations suggest that consciousness itself might play a fundamental role in determining physical reality. Others propose that every quantum measurement creates parallel universes where all possible outcomes occur simultaneously. Still others argue that the wave function never actually collapses, but that quantum decoherence creates the appearance of classical behavior without invoking mysterious measurement effects. These aren't just abstract theoretical debates, they have practical implications for technologies that are reshaping our world. Quantum computers exploit superposition states to perform calculations impossible with classical logic. Quantum cryptography uses measurement-induced changes to detect eavesdropping on secure communicati. Quantum sensors achieve precision beyond classical limits by carefully controlling how quantum systems are observed. Understanding how particles behave when observed is becoming essential for navigating our increasingly quantum technological civilization. If you're ready to dive into the strange world where observation itself changes reality, subscribe and hit the thumbs up button. And here's something to consider as we begin. If quantum particles change behavior when observed, what does that suggest about the role of consciousness in physical reality? Comment below with your thoughts on whether the universe might somehow be aware of when it's being watched. I'll pin the most thought-provoking response. This exploration will take us from the most precisely controlled laboratory experiments ever conducted to the deepest philosophical questions about the nature of existence itself. We'll examine how particle accelerators, quantum computers, and ultra-sensitive detectors reveal the strange behavior of observed quantum systems. We'll explore competing interpretations of quantum mechanics that range from multiple parallel realities to the idea that consciousness creates physical reality through the act of observation. By the end of this journey, you'll understand that observation isn't passive, it's an active process that fundamentally shapes the quantum world around us. Whether you're looking at this screen, breathing air, or simply existing as a conscious being in a quantum universe, you're participating in the ongoing creation of reality through countless quantum measurements occurring throughout your body every nanosecond. Now let us begin our exploration of the most mysterious aspect of quantum mechanics, how the simple act of looking changes everything about what we're looking at. Wave collapse. Imagine holding a coin in your palm, but instead of showing heads or tails, it somehow displays both sides simultaneously until the moment you decide to look at it. At that instant, the coin chooses one face or the other, as if your observation forced it to make a decision it had been avoiding. This impossible scenario perfectly describes how quantum particles behave when observed, revealing one of the most profound mysteries in physics, the collapse of the wave function. Before we can understand how observation changes quantum behavior, we need to grasp what quantum particles are like when nobody's watching, and like the solid, definite objects of our everyday experience. Unobserved quantum particles exist as probability waves spread throughout space and time. These aren't just mathematical abstractions, they represent the actual physical state of particles before measurement forces them into specific configurations. Picture an electron orbiting an atomic nucleus. Classical physics would describe this as a tiny ball following a definite circular or elliptical path, like a miniature planet around a star. But quantum mechanics reveals something far stranger. The electron doesn't follow any particular path at all. Instead, it exists as a cloud of probability, with different regions having different likelihoods of containing the electron when measured. This probability cloud, described mathematically by the wave function, represents all possible states the electron might be found in simultaneously. The wave function contains complete information about a quantum system's possible states, but it doesn't predict exactly what you'll find when you measure the system. Instead, it gives probabilities for different measurement outcomes. For an electron around a hydrogen atom, the wave function might indicate a 30% chance of finding the electron in one region, 50% in another, and 20% in a third location. These aren't simply limitations of our knowledge. Quantum mechanics suggests the electron genuinely exists in all these states at once until observation forces a definite outcome. This superposition principle was first clearly articulated by Erwin Schrödinger, who developed the mathematical framework describing quantum wave functions. Schrodinger's equation predicts how these probability waves evolve over time, spreading out, interfering with each other, and creating complex patterns of quantum possibilities. But the equation says nothing about what happens during measurement, how the smooth, deterministic evolution of the wave function suddenly becomes the random, definite outcomes we observe in experiments. The measurement problem represents one of the deepest puzzles in quantum mechanics. When you measure a quantum system, something dramatic happens. The wave function instantly collapses from a superposition of many possible states into a single, definite state corresponding to your measurement result. If the wave function gave a 30% probability of finding an electron in a particular region, and your measurement detects it there, the wave function immediately becomes 100% localized in that region and 0% everywhere else. This collapse process seems to violate everything else we know about physics. The Schrödinger equation that governs wave function evolution is completely deterministic and reversible. You can calculate exactly how the wave function will change over time, and you can run the calculation backward to determine past states from present ones. But wave function collapse introduces an irreversible, random element that appears nowhere else in the fundamental equations of quantum mechanics. Consider what happens during a typical quantum measurement. Suppose you're measuring the spin of an electron, which can be either up or down relative to any chosen direction. Before measurement, quantum mechanics says the electron exists in a superposition of both spin states simultaneously. It is spinning both up and down until you force it to choose one orientation. Your measurement apparatus, perhaps a carefully aligned magnetic field, interacts with the electron's quantum state and somehow causes the superposition to collapse into a definite outcome. But here's where the mystery deepens. We don't know exactly what constitutes a measurement in quantum mechanics. Does the electron's wave function collapse when it first encounters the magnetic field? When the magnetic field's atoms become entangled with the electron? When the measurement apparatus registers a result? When a conscious observer reads the result? The boundary between quantum superposition and classical definiteness remains one of the most contentious issues in physics. Different interpretations of quantum mechanics propose radically different explanations for wave function collapse. The Copenhagen interpretation, developed by Niels Bohr and Werner Heisenberg, treats measurement as a fundamental aspect of quantum mechanics that cannot be reduced to more basic physical processes. In this view, the wave function collapse is a basic feature of nature that occurs whenever a quantum system interacts with a classical measurement apparatus. The many worlds interpretation, proposed by Hugh Everett III, suggests that wave functions never actually collapse. Instead, every possible measurement outcome occurs in parallel universes, and we experience only one branch of an ever-splitting multiverse. From this perspective, when you measure an electron spin, the universe splits into parallel realities where the electron has every possible spin orientation. You experience the outcome in your particular branch, while countless copies of yourself in parallel branches experience different outcomes. More recent decoherence theory attempts to explain apparent wave function collapse through the quantum system's interactions with its environment. According to this approach, quantum superposition states are extremely fragile and rapidly become entangled with surrounding atoms, photons, and fields. This environmental entanglement effectively destroys the coherent superposition, making the system appear to have definite properties even though the wave function remains. Technically, in superposition, laboratory experiments have revealed incredible precision with which wave function collapse occurs. In quantum optics experiments, individual photons can be prepared in superposition states where they simultaneously take multiple paths through an optical apparatus. Photodetectors at different locations can measure which path each photon actually followed, causing the wave function to collapse from a superposition of all possible paths into a definite path corresponding to whichever detector fires. Recent advances in quantum technology have enabled scientists to observe wave function collapse in real time using ultra-fast measurement techniques. Experiments with superconducting quantum devices can track how superposition states evolve and collapse over time scales of nanoseconds or even picoseconds. These measurements reveal that collapse isn't instantaneous but occurs over finite time periods, determined by the strength of the measurement interaction. Perhaps most remarkably, Quantum control experiments have demonstrated that measurement strength can be continuously adjusted. Weak measurements can extract partial information about quantum systems without causing complete wave function collapse, allowing multiple measurements on the same quantum state. Strong measurements cause immediate collapse, while measurements of intermediate strength create partial collapse states that retain some quantum coherence while acquiring some classical properties. The study of wave function collapse has practical applications in emerging quantum technologies. Quantum computers rely on maintaining coherent superposition states while preventing unwanted collapse from environmental noise or measurement backaction. Quantum error correction protocols use careful measurement strategies to detect and correct errors without destroying the quantum information being processed. Understanding precisely how observation causes collapse is essential for building reliable quantum devices. What wave function collapse reveals about quantum measurement goes far beyond technical physics into fundamental questions about the nature of reality. If particles exist in multiple states simultaneously until observed, what does this say about the role of consciousness or information in determining physical reality? The act of observation appears to play a creative role in establishing the classical world we experience from the quantum possibilities that exist before measurement. This exploration of wave function collapse sets the stage for understanding an even more mysterious aspect of quantum behavior: how particles seem to know what type of measurement will be performed and adjust their behavior accordingly. How can quantum systems appear to respond to future measurement choices in ways that seem to violate our understanding of causality? Observer effect. In 1801, Thomas Young performed an experiment that should have settled the question of light's fundamental nature once and for all. He shone light through two narrow parallel slits and observed the resulting pattern on a distant screen. If light consisted of particles, he expected to see two bright strips corresponding to each slit. Instead, he observed an intricate pattern of alternating bright and dark bands, an interference pattern that could only result if light waves passing through both slits were interfering with each other. For over a century, this double-slit experiment provided conclusive evidence that light was purely a wave phenomenon. But the quantum revolution revealed that Young's experiment was only half the story. When modern physicists repeated the double-slit experiment using detectors sensitive enough to observe individual photons, they discovered something impossible: single particles of light were somehow interfering with themselves. Each photon, fired one at a time through the apparatus, somehow passed through both slits simultaneously and interfered with itself to create the familiar wave pattern. Yet the moment scientists placed detectors to see which slit each photon actually used, the interference pattern vanished completely. This observer effect represents one of the most profound and unsettling discoveries in physics. Quantum particles don't simply have hidden properties that measurement reveals. The very act of observation fundamentally changes what the particles are doing. When you're not watching, photons behave like waves that can pass through multiple paths simultaneously. When you are watching, they behave like particles that must choose one path or another. The quantum world seems to respond to whether or not you're paying attention. Modern versions of the double-slit experiment have pushed this mystery to even more extreme levels. In delayed choice experiments, physicists can decide whether to measure which path information after photons have already passed through the slits but before they reach the final detection screen. Remarkably, the choice of whether to perform path detection made after the photons have supposedly committed to being waves or particles retroactively determines whether interference patterns appear or disappear. John Wheeler, one of the most influential theoretical physicists of the 20th century, proposed even more mind-bending variations in his delayed choice quantum eraser experiments. Path information can be measured and then erased by subsequent quantum measurements. When path information is erased, interference patterns reappear as if the photons knew which path information would be destroyed and adjusted their behavior accordingly. These experiments suggest that the distinction between wave and particle behavior isn't determined when photons pass through the slits, but rather by the complete measurement setup including future detection choices. The observer effect extends far beyond optical experiments to every aspect of quantum mechanics. When measuring an electron's position very precisely, you inevitably disturb its momentum due to the quantum uncertainty principle. The more accurately you determine where an electron is located, the more uncertain its velocity becomes, and vice versa. This is the limitation of measurement technology. It is a fundamental feature of quantum reality that emerges from the wave nature of matter itself. Consider how quantum systems respond to different types of observation. If you measure an electron spin along one direction, you get a definite result: spin up or spin down. But this measurement completely randomizes the electron's spin component in perpendicular directions. The act of gaining information about one quantum property necessarily destroys information about other properties. Quantum measurement is like asking questions that force systems to forget answers to other questions they might have known previously. This complementarity principle, formulated by Niels Bohr, reveals that quantum systems cannot simultaneously possess well-defined values for certain pairs of properties. Position and momentum are complementary, as are different components of angular momentum and many other quantum observables. The observer effect emerges from this fundamental limitation. Measuring one property of a quantum system necessarily disturbs other properties in predictable but unavoidable ways. But the observer effect involves more than just measurement disturbance. It reveals that quantum systems genuinely don't have definite properties until observed. This isn't because particles are too small to observe without disturbance, but because the act of observation plays a constitutive role in determining what properties exist. Before measurement, quantum systems exist in superposition states that combine multiple contradictory possibilities. Observation doesn't reveal pre-existing properties, it creates the properties we observe. Recent experiments have demonstrated observer effects at increasingly macroscopic scales. Researchers have created quantum superposition states involving entire molecules containing hundreds of atoms, demonstrating interference effects for objects much larger than individual electrons or photons. These molecular interferometry experiments show that the boundary between quantum and classical behavior isn't determined by size alone, but by the degree of observation and environmental interaction. The development of quantum non-demolition measurements has revealed subtle aspects of the observer effect that aren't captured by simple measurement. Disturbs the system explanations. Q&D measurements can extract information about certain quantum properties without disturbing those particular properties, though they necessarily disturb other complementary properties. These techniques enable repeated measurements of the same quantum observable, revealing how quantum states evolve under continuous observation. Quantum Zeno effect experiments have shown that frequent observation can actually freeze quantum evolution. Just as Zeno's paradox suggests that motion becomes impossible if divided into infinitely many instants, frequent quantum measurements can prevent systems from evolving between observations. Conversely, the quantum anti-Zeno effect shows that certain measurement protocols can accelerate quantum evolution. These phenomena demonstrate that observation frequency and timing can dramatically affect quantum behavior. The observer effect has profound implications for quantum computing and information processing. Quantum computers rely on maintaining coherent superposition states while preventing unwanted observation by environmental noise, every stray photon, thermal fluctuation, or electromagnetic field can act as an unintended observer that collapses quantum coherence and destroys computational information. Building practical quantum computers requires extraordinarily careful isolation from all forms of environmental observation. Quantum cryptography exploits the observer effect for absolute communication security. Any attempt to eavesdrop on quantum encrypted messages necessarily disturbs the quantum states being transmitted, revealing the presence of interception. This isn't due to technological limitations, it is a fundamental consequence of quantum mechanics that guarantees detection of any unauthorized observation attempts. The philosophical implications of the observer effect challenge our most basic assumptions about objective reality. If measurement fundamentally changes what we're measuring, what does this say about the nature of scientific knowledge? Classical science assumed that careful observation could reveal the objective properties of an independent reality. Quantum mechanics suggests that observation and reality are so intimately connected that the boundary between subject and object becomes meaningless. Some interpretations of quantum mechanics propose that consciousness itself plays a fundamental role in the observer effect. The consciousness-based interpretation suggests that wave function collapse occurs specifically when conscious observers become aware of measurement results, not during the physical interaction between quantum systems and measurement apparatus. While this interpretation remains controversial, it highlights how quantum mechanics connects physics to fundamental questions about mind and awareness. Alternative interpretations attempt to eliminate the observer effect by proposing that observation never actually changes quantum systems. The many-worlds interpretation suggests that all possible measurement outcomes occur simultaneously in parallel universes, and observers simply find themselves in one branch of the multiverse. Hidden variable theories propose that quantum systems have definite properties all along, but these properties are non-local and contextual in ways that create the appearance of observer effects. What the observer effect reveals about quantum measurement extends far beyond laboratory curiosities to fundamental questions about the relationship between knowledge and reality. Every time you observe the world around you, seeing photons reflected from objects, feeling pressure from molecular impacts, hearing sound waves propagated through air, you are participating in quantum measurement processes that help define the classical reality you experience. This understanding of how observation shapes quantum behavior sets the stage for exploring an even stranger aspect of quantum reality: how measuring quantum systems can reveal properties that seem to contradict each other depending on which measurements you choose to perform. How can the same quantum system display completely different natures depending on which questions you ask it? Quantum measurement: what happens when you try to measure something that exists in multiple contradictory states simultaneously? This isn't just a philosophical thought experiment, it's the central challenge of quantum measurement theory, where scientists have learned to extract definite information from systems that fundamentally resist having definite properties. The art and science of quantum measurement reveals not just how to observe quantum systems, but how the very act of asking specific questions shapes the reality that responds. Consider the most basic quantum measurement: detecting whether a photon is present at a particular location. Classical intuition suggests this should be straightforward: either the photon is there, or it isn't. But quantum mechanics reveals that the photon might exist in a superposition state where it is simultaneously present and absent until your detector forces it to choose one state or the other. The measurement outcome isn't predetermined, it is created through the interaction between the quantum system and your measurement apparatus. The mathematical framework of quantum measurement, developed by John von Neumann and others, describes this process with startling precision. Before measurement, a quantum system exists in a superposition state described by its wave function. The measurement apparatus, described by its own quantum state, interacts with the system being measured. This interaction creates entanglement between the system and apparatus, evolving into a combined quantum state that contains correlations between system properties and apparatus readings. But here is where quantum measurement becomes truly mysterious. The final step, where definite measurement outcomes emerge, cannot be described by the same quantum evolution that governs all other physical processes. The smooth, deterministic Schrödinger equation that predicts how quantum states evolve over time suddenly gives way to a random, irreversible collapse that selects one outcome from many possibilities. This measurement postulate represents an additional rule that must be added to quantum mechanics to connect quantum possibilities with classical observations. Different types of quantum measurements reveal different aspects of the same system, often in mutually exclusive ways. A quantum particle's position and momentum cannot be simultaneously measured with perfect precision due to Heisenberg's uncertainty principle. But this isn't merely a technological limitation, it reflects the fundamental nature of quantum reality. Measuring position precisely requires interactions that necessarily disturb momentum, and vice versa. The act of measurement itself determines which aspects of quantum reality become accessible. Consider how quantum spin measurements work. An electron's spin can be measured along any direction in space, but each measurement reveals only one component of the total spin vector. Measuring spin along the z-axis gives a definite result up or down, but this measurement completely randomizes the electron's spin components along the x and y axes. If you subsequently measure spin along the x-axis, you'll get a random result that's uncorrelated with the previous z-axis measurement. The electron spin state has been fundamentally altered by the first measurement. This measurement-dependent reality extends to more complex quantum properties. In quantum optics, photons can be measured for their polarization, frequency, arrival time, or spatial distribution. Each measurement reveals definite information about one property while necessarily obscuring information about complementary properties. A measurement that precisely determines a photon's frequency must take extended time, making its arrival time uncertain. Conversely, measuring precise arrival time requires short interaction duration that makes frequency uncertain. Modern quantum measurement techniques have achieved extraordinary precision and control. Quantum non-demolition measurements can repeatedly measure the same quantum property without disturbing it, enabling continuous monitoring of quantum evolution. These Q&D techniques work by coupling the quantum system to auxiliary systems in ways that preserve the measured property while extracting information through the auxiliary system as state changes. Weak measurement protocols can extract partial information about quantum systems without causing complete wave function collapse. By using very gentle interactions between quantum systems and measurement apparatus, scientists can learn something about quantum properties while preserving enough quantum coherence for subsequent measurements. These techniques enable measurement of quantum trajectories, the paths individual quantum systems follow through state space during evolution, the development of positive operator valued measures. POV-MIS has generalized quantum measurement beyond simple yes/no questions to complex multi-outcome measurements. POVM theory describes how to optimally extract information from quantum systems when direct measurement of desired properties isn't possible. These generalized measurements enable quantum state tomography, the complete reconstruction of a known quantum states through carefully chosen measurement sequences. Single-shot quantum measurements reveal individual quantum events rather than statistical averages over many repetitions. These measurements require extraordinarily sensitive detectors capable of registering individual photons, electrons, or atoms with near-perfect efficiency. Single photon detectors using superconducting nanowires or transition edge sensors can detect individual light quanta with timing precision approaching fundamental quantum limits. Quantum measurement backaction, the unavoidable disturbance that measurements create, has become a central concern for quantum technology development. Every quantum measurement necessarily entangles the measured system with the measurement apparatus, creating correlations that can persist long after the measurement is completed. Understanding and controlling this backaction is essential for building quantum computers, quantum sensors, and quantum communication systems. The measurement problem in quantum foundations asks fundamental questions about when and why wave function collapse occurs. Does collapse happen when quantum systems interact with measurement apparatus? When apparatus states become macroscopically distinguishable? When conscious observers become aware of results? Or does collapse never actually occur, with apparent randomness emerging from branching into parallel worlds? Different interpretations provide radically different answers. Recent advances in quantum control have enabled real-time feedback protocols where measurement results immediately influence subsequent quantum evolution. These measurement-based quantum control schemes can stabilize desired quantum states, protect against environmental disturbance, and implement quantum error correction. The ability to measure and respond to quantum systems in real time is revolutionizing practical quantum technology. Quantum error correction protocols use syndrome measurements to detect quantum errors without learning the quantum information being protected. These clever measurement schemes can determine what type of error occurred without revealing the actual quantum state, enabling error correction while preserving quantum coherence. Understanding how to measure error syndromes without destroying quantum information is crucial for building large-scale quantum computers. The complementarity between different quantum measurements reflects deeper symmetries in quantum mechanics. Mutually unbiased basis measurement directions that are maximally incompatible with each other play central roles in quantum cryptography, quantum state tomography, and tests of quantum non-locality. These mathematical structures reveal how quantum measurement incompatibilities arise from the geometric structure of quantum state space itself. Bell-type measurements that reveal quantum entanglement and non-locality represent some of the most profound applications of quantum measurement theory. These measurements can distinguish between quantum systems that are merely classically correlated and those displaying genuine quantum entanglement. The ability to reliably measure and verify quantum entanglement is essential for quantum communication and quantum computing applications. What quantum measurement reveals about the relationship between questions and answers in quantum mechanics challenges classical notions of objective reality. And like classical systems that have definite properties independent of observation, quantum systems seem to respond to the specific questions being asked through measurement choices. The answers you get depend not just on the system's state, but on which measurements you decide to perform. This contextual nature of quantum measurement connects to fundamental questions about information and reality. Each quantum measurement extracts specific information from quantum systems while necessarily erasing other potential information. The total amount of information that can be extracted from any quantum system is limited by quantum uncertainty relations, suggesting that information itself might be a more fundamental concept than classical properties, like position and momentum. Understanding quantum measurement theory prepares us to explore an even more puzzling aspect of quantum behavior: how quantum systems can exist in multiple contradictory states simultaneously before measurement forces them to exhibit definite properties. What does it mean for particles to be in superposition, and how does this strange state of existence shape everything we observe in the quantum world? Superposition states imagine existing in multiple realities simultaneously, being in your living room and your kitchen at the same time, reading this sentence while also watching television, experiencing every possible version of your current moment until something forces you to collapse into just one of them. This impossible scenario perfectly describes the everyday existence of quantum particles, which routinely exist in superposition states that combine multiple contradictory possibilities until observati on forces them to choose a single reality. Superposition represents perhaps the most counterintuitive aspect of quantum mechanics. And like classical objects that must be in definite states, a coin shows either heads or tails. A light switch is either on or off. Quantum systems can exist in coherent combinations of multiple states simultaneously. An electron can spin both clockwise and counterclockwise at the same time. A photon can be both vertically and horizontally polarized. An atom can be both excited and unexcited until measurement forces it into one configuration or another. The mathematical description of superposition reveals its profound nature. In quantum mechanics, the state of any system is described by a wave function that can be written as a sum of different possible states, each weighted by a complex number called an amplitude. For a particle that can be in location or location B, the superposition state might be written as 60% of state A plus 80% of state B. But these aren't classical probabilities. The amplitudes are complex numbers that can interfere with each other in ways impossible for ordinary probabilities. This interference between different components of superposition states creates the most distinctive features of quantum behavior. When a particle in superposition encounters a barrier with two openings, the components corresponding to different paths can interfere constructively in some regions and destructively in others, creating the characteristic wave patterns observed in interference experiments. The particle isn't really taking one path or the other, it's genuinely taking all possible paths simultaneously until measurement collapses the superposition. Superposition states. Schrödinger famously illustrated the strangeness of superposition through his thought experiment involving a cat that could be simultaneously alive and dead. While intended as a critique of quantum mechanics, Schrödinger's cat has become the archetypal example of macroscopic superposition. In the thought experiment, a quantum measurement triggers a mechanism that either kills or spares a cat, leaving the cat in a superposition of alive and dead states until someone opens the box to check. Modern experiments have created increasingly macroscopic superposition states that push the boundaries between quantum and classical behavior. Researchers have demonstrated superposition states involving entire molecules containing hundreds of atoms, showing interference patterns that prove these complex objects exist in multiple locations simultaneously. Superconducting quantum devices can exist in superposition states where electrical currents flow in opposite directions at the same time, creating Schrödinger cat states with macroscopic electrical properties. The fragility of superposition states reveals why we don't observe quantum behavior in everyday life. Any interaction with the environment, collisions with air molecules, absorption of thermal radiation, coupling to electromagnetic fields can destroy quantum superposition through a process called decoherence. The larger and warmer an object becomes, the faster it loses quantum coherence and settles into definite classical states. This explains why quantum effects dominate atomic scales but disappear for macroscopic objects. But understanding decoherence has enabled scientists to create and maintain superposition states under increasingly challenging conditions. By isolating quantum systems from environmental disturbance through ultra-high vacuum, cryogenic cooling, and electromagnetic shielding, researchers can preserve superposition states for extended periods. Some quantum systems, like certain atomic clocks and superconducting devices, can maintain coherent superposition for hours or even days under optimal conditions. The ability to create and control superposition states has become the foundation for revolutionary quantum technologies. Quantum computers exploit superposition to perform calculations on multiple input values simultaneously. While a classical computer must process each possible input separately, a quantum computer in superposition can explore all possibilities in parallel, potentially providing exponential speed-up for certain types of calculations. Quantum sensing applications use superposition states to achieve measurement precision beyond classical limits. By placing quantum sensors in superposition states that are sensitive to external fields, researchers can detect magnetic fields, gravitational variations, and other environmental changes with sensitivity approaching fundamental quantum limits. These quantum-enhanced sensors are enabling new types of medical imaging, geological surveying, and fundamental physics experiments. The coherent control of superposition states requires extraordinary precision in quantum manipulation techniques. Researchers use precisely timed laser pulses, carefully calibrated magnetic fields, and other control methods to rotate quantum states through superposition space with accuracy better than 1 part in a million. These control techniques enable quantum gate operations for quantum computing and quantum state preparation for fundamental physics experiments. Different types of superposition reveal various aspects of quantum behavior. Spatial superposition involves particles existing in multiple locations simultaneously, as demonstrated in matter-wave interferometry experiments with atoms, molecules, and even small crystallites. Energy superposition creates quantum systems with indefinite energy that can absorb or emit photons in ways impossible for classical systems. Angular momentum superposition allows particles to spin in multiple directions simultaneously. Quantum superposition exhibits non-classical correlations that have no analog in ordinary experience. Entangled superposition states can involve multiple particles existing in correlations that transcend classical physics, where measuring one particle instantly affects the superposition state of distant particles. These entangled superpositions form the basis for quantum teleportation, quantum cryptography, and tests of quantum non-locality. The measurement of superposition states reveals the fundamental randomness of quantum mechanics. When you measure a particle in superposition, you get one of the possible outcomes with probabilities determined by the quantum amplitudes, but the specific outcome is genuinely random. No hidden variables or additional information can predict which outcome will occur in any individual measurement, though the statistical distribution over many measurements is precisely determined by the superposition state. Recent developments in quantum state tomography enable complete characterization of superposition states through carefully designed measurement sequences. By performing many different types of measurements on identically prepared superposition states, researchers can reconstruct the full quantum wave function, including all phases and amplitudes. This tomographic reconstruction reveals the complete structure of quantum superposition with extraordinary precision. The creation of cat states, macroscopic superposition states analogous to Schrödinger's cat, has become a major focus of quantum research. These states involve macroscopic quantum systems existing in superposition of dramatically different configurations. Superconducting ket states can involve electrical currents flowing in opposite directions. Optical ket states can involve light fields with opposite phases. And atomic ket states can involve collections of atoms in opposite spin configurations. Superposition states challenge our understanding of the relationship between microscopic quantum mechanics and macroscopic classical reality. The superposition principle suggests that everything, including macroscopic objects and conscious observers, should obey quantum mechanics and exist in superposition states. Yet our everyday experience involves only definite classical properties. Understanding how classical reality emerges from quantum superposition remains one of the deepest problems in physics. The decoherence program attempts to explain the classical world through environmental entanglement that effectively destroys macroscopic superposition without invoking fundamental measurement postulates. According to this view, objects appear classical not because they actually lose superposition, but because environmental interactions make different superposition components effectively inaccessible. The quantum superposition persists, but becomes practically unobservable. Alternative interpretations propose that superposition states represent genuine ontological plurality. Particles really do exist in multiple states simultaneously until measurement creates a single reality. The many worlds interpretation suggests that all components of superposition states are equally real, existing in parallel branches of reality that observers experience separately. From this perspective, measurement doesn't destroy superposition, but rather selects which branch of reality you experience. What superposition states reveal about quantum reality extends far beyond laboratory physics to fundamental questions about the nature of existence and possibility. If particles can exist in multiple contradictory states simultaneously, what does this suggest about the structure of reality itself? Understanding superposition prepares us to explore an even stranger quantum phenomenon: how particles can become correlated in ways that transcend space and time through quantum entanglement. Entanglement effects. Einstein called it spooky action at a distance, and spent years trying to prove it couldn't exist. Yet quantum entanglement has become not only one of the most thoroughly verified phenomena in physics, but also the foundation for revolutionary technologies that promise to transform computation, communication, and our understanding of reality itself. When quantum particles become entangled, they form connections so intimate that measuring one particle instantaneously affects the other, regardless of the distance separating them, even if they're on opposite sides of the galaxy. Entanglement emerges naturally whenever quantum systems interact and then separate while maintaining quantum coherence. Consider two photons created simultaneously in an atomic decay process. If the atom's initial angular momentum was zero, conservation laws require that the two photons carry equal and opposite spins. But quantum mechanics says that each photon exists in the superposition of both possible spin states until measured. The remarkable consequence is that the two photons share a single, extended quantum state that encompasses both particles simultaneously. This shared quantum state creates correlations that transcend classical physics. When you measure the first photon and find it spinning clockwise, you instantly know that the second photon, no matter how far away, must be spinning counterclockwise. But here's what makes this genuinely quantum: before your measurement, neither photon had definite spin. The measurement of the first photon doesn't reveal a pre-existing property, it creates a definite reality for both particles simultaneously, even across cosmic distances. The mathematical description of entanglement reveals its profound non-classical nature. Entangled states cannot be written as products of separate quantum states for each particle. Instead, they form irreducible wholes where the particles lose their individual identities and become aspects of a single, extended quantum system. This mathematical inseparability corresponds to physical reality. Entangled particles genuinely don't have separate existences until measurement breaks the entanglement. Bell's theorem, developed by physicist John Stuart Bell in 1964, proved that entanglement creates correlations stronger than any possible classical mechanism. Bell showed that if particles had definite properties before measurement, even if those properties were hidden from direct observation, the correlations between distant measurements could never exceed certain mathematical bounds. But quantum entanglement routinely violates these Bell inequalities, demonstrating that quantum reality fundamentally differs from classical intuitions about local realism. Alain Aspect's groundbreaking experiments in the early 1980s provided the first decisive confirmation of Bell inequality violations using entangled photons. These experiments used rapidly changing measurement directions to prevent any classical communication between measurement apparatus, definitively ruling out local hidden variable explanations for quantum correlations. Subsequent experiments by teams led by Anton Zeilinger, John Clauser, and others have closed every conceivable loophole, confirming that quantum entanglement really does transcend classical locality. Modern entanglement experiments routinely achieve near-perfect correlation strengths and operate over increasingly vast distances. Quantum communication satellites have demonstrated entanglement between space-based and ground-based systems across thousands of kilometers. The Chinese Maisha satellite has created entangled photon pairs in space and distributed them to ground stations separated by over 1,200 kilometers, proving that entanglement works even through the harsh environment of space. But entanglement involves much more than simple two-particle correlations. Multi-particle entanglement creates quantum states where 3, 4, or even hundreds of particles share extended quantum correlations that have no classical analog. These multi-particle entangled states, called GHZ states after Greenberger, Horn, and Zeilinger, exhibit correlations that violate classical locality even more dramatically than two-particle systems. The largest entangled systems created in laboratories now involve hundreds of atoms, ions, or photons existing in shared quantum states. These macroscopic entangled systems push the boundaries between quantum and classical physics, demonstrating that quantum correlations can persist even in systems large enough to observe with conventional microscopes. Some theoretical proposals suggest that certain biological systems might exploit quantum entanglement for enhanced efficiency in photosynthesis or other biological processes. Quantum computing relies fundamentally on entanglement to achieve computational advantages over classical systems. While classical computers process information using independent bits that are either 0 or 1, quantum computers use quantum bits qubits that can exist in superposition and become entangled with each other. The entanglement between qubits creates exponentially complex quantum correlations that enable quantum algorithms to solve certain problems exponentially faster than any classical approach. The power of quantum computing emerges from controlled entanglement dynamics. Quantum algorithms, like Shor's factoring algorithm and Grover's search algorithm, work by creating specific entangled states that encode solutions to computational problems. The measurement process then extracts classical information from these entangled quantum states, revealing solutions that would require astronomical time to compute classically. Quantum error correction exploits entanglement to protect quantum information from environmental decoherence by entangling logical quantum information across multiple physical qubits. Quantum error correction can detect and correct errors without learning the quantum information being protected. These entangled error correction codes enable building large-scale quantum computers despite imperfect individual quantum components. Quantum cryptography uses entanglement to create unbreakable communication security. The BB84 protocol and related quantum key distribution schemes rely on the fundamental impossibility of copying unknown quantum states to detect eavesdropping attempts. Any interception of quantum encrypted communications necessarily disturbs the entangled quantum states, revealing the presence of unauthorized observers through measurable changes in correlation statistics. CEAS. Quantum teleportation. The transfer of quantum information from one location to another without physical transport represents perhaps the most striking application of entanglement. By measuring entangled particles in special ways, complete quantum states can be transmitted across arbitrary distances using only classical communication and pre-shared entanglement. While no matter or energy travels during quantum teleportation, the quantum information defining a particle's state is genuinely transferred from one location to another. The study of entanglement has revealed deep connections between quantum information and fundamental physics. Black hole thermodynamics appears to involve entanglement between quantum states inside and outside event horizons. The holographic principle suggests that all information in any volume of space might be encoded on its boundary through entanglement structures. Some theories propose that spacetime itself might emerge from entanglement patterns in more fundamental quantum systems. Entanglement also reveals the contextual nature of quantum reality. The correlations between entangled particles depend on which measurements observers choose to perform, demonstrating that quantum properties aren't simply revealed by measurement but actually depend on measurement contexts. This contextuality challenges classical notions of objective reality independent of observation. Recent developments in quantum metrology use entanglement to achieve measurement precision beyond classical limits. Entangled sensors can measure magnetic fields, gravitational waves, and other physical quantities with sensitivity approaching fundamental quantum bounds. These quantum-enhanced sensors exploit entanglement to reduce noise and increase sensitivity in ways impossible with classical measurement strategies. The generation and detection of entanglement requires extraordinary experimental control and precision. Entangled photon sources use nonlinear optical processes to create photon pairs with precisely correlated properties. Ion trap systems use laser cooling and electromagnetic fields to create entangled atomic states with near-perfect fidelity. Superconducting quantum devices can create and manipulate entangled electrical states that persist for extended periods. Bell test experiments continue to explore the foundations of quantum mechanics by testing increasingly subtle aspects of entanglement and locality. Recent experiments have achieved loophole-free Bell tests that close all known classical explanations for quantum correlations. Others explore whether conscious choice in measurement settings affects quantum correlations, testing the relationship between free will and quantum mechanics. What entanglement reveals about quantum reality extends beyond physics into fundamental questions about the nature of information, consciousness, and reality. If distant particles can share immediate correlations regardless of spatial separation, what does this suggest about the structure of space and time? Understanding entanglement prepares us to explore how these strange quantum correlations affect our macroscopic world and technological civilization. Measurement paradox is what happens when quantum mechanics meets philosophy. You get some of the most mind-bending paradoxes in all of science thought experiments that reveal how quantum measurement challenges our most basic assumptions about reality, logic, and the nature of existence itself. These aren't merely academic puzzles, they illuminate fundamental contradictions between quantum behavior and classical reasoning that continue to drive theoretical physics and practical quantum technology development. The most famous measurement paradox emerged from Erwin Schrödinger's 1935 thought experiment designed to illustrate what he saw as the absurdity of quantum mechanics when applied to macroscopic objects. Schrödinger imagined a diabolical device, a quantum system, perhaps a radioactive atom with exactly 50% probability of decaying within 1 hour, connected to a mechanism that would break a flask of poison if decay occurred. A cat placed in the sealed box would be killed if the atom decayed, or remain alive if it didn't. According to quantum mechanics, the undecayed atom exists in the superposition of decayed and undecayed states until observed. This means the entire system, including the cat, should exist in a superposition of alive and dead states until someone opens the box to check. But conscious experience never reveals cats that are simultaneously alive and dead. We always find the cat in one definite state or the other. This measurement paradox reveals the mysterious boundary between quantum superposition and classical definiteness. Schrödinger's cat illustrates the measurement problem. How and when does quantum superposition collapse into definite classical states? Different interpretations of quantum mechanics provide radically different answers. The Copenhagen interpretation treats measurement as a fundamental process that occurs when quantum systems interact with classical apparatus. But what constitutes a classical system? And how can classical systems exist if everything is ultimately composed of quantum particles? The many worlds interpretation eliminates measurement paradoxes by proposing that superposition never actually collapses. In Everett's multiverse, the cat exists in both alive and dead states in parallel branches of reality. When you open the box, the universe splits into separate branches where you observe each possible outcome. From your perspective in any particular branch, the cat appears to have a definite state, but both outcomes are equally real in the complete quantum multiverse. An even stranger measurement paradox emerges from quantum delayed choice experiments. John Wheeler proposed scenarios where the decision to measure particle or wave properties could be made after photons had already decided what type of behavior to exhibit. In these experiments, photons pass through apparatus that can be configured to reveal either wave or particle behavior. But the configuration choice is made only after photons have supposedly committed to their behavior. Remarkably, delayed choice experiments show that photons seem to know retroactively what type of measurement will be performed. If you decide to measure wave properties after photons have passed through a double-slit apparatus, interference patterns appear as if the photons had been waves all along. If you decide to measure which path information, the interference disappears as if the photons had been particles from the beginning. The measurement choice seems to retroactively determine the nature of past quantum events. Quantum eraser experiments push this paradox to even greater extremes. In these setups, which path information can be measured and then erased by subsequent quantum measurements. When the erasure occurs, interference patterns reappear even though the photons had previously been measured as particles. These experiments suggest that quantum properties aren't determined when events occur, but rather by the complete measurement context including future detection choices. The PR paradox, proposed by Einstein, Podolsky, and Rosen in 1935, challenged quantum mechanics through entanglement measurements. They argued that if quantum mechanics were complete, measuring one particle in an entangled pair would instantaneously affect the other particle regardless of distance. Since such spooky action at a distance seemed impossible, they concluded that quantum mechanics must be incomplete, with hidden variables determining measurement outcomes. Bell's theorem proved that the PR argument actually reveals the fundamental non-locality of quantum mechanics rather than its incompleteness. Local hidden variable theories cannot reproduce the correlations observed in entangled quantum systems. The experimental violation of Bell inequalities demonstrates that quantum correlations genuinely transcend classical locality, confirming that measurement of one entangled particle really does instantaneously affect its distant partner. Modern versions of measurement paradoxes continue to challenge our understanding. The quantum Zeno paradox shows that frequent measurement can freeze quantum evolution, preventing systems from changing states between observations. Conversely, the anti-Zeno effect demonstrates that certain measurement protocols can accelerate quantum evolution. These phenomena reveal that observation timing and frequency can dramatically affect quantum behavior in counterintuitive ways. The Wigner's friend paradox explores the role of consciousness in quantum measurement. Eugene Wigner imagined his friend observing a quantum measurement inside an isolated laboratory. From Wigner's external perspective, the entire laboratory including his friend exists in quantum superposition until Wigner makes an observation. But the friend inside the lab experiences definite measurement outcomes without Wigner's observation. This paradox questions whether conscious experience requires wave function collapse or whether consciousness can exist in superposition. Recent theoretical developments have created even more sophisticated measurement paradoxes. Frottiger and Renner's theorem demonstrates that different observers in quantum mechanics can reach contradictory conclusions about measurement outcomes, even when using perfectly consistent reasoning. Their proof shows that certain combinations of quantum mechanics principles lead to logical contradictions that challenge the notion of objective reality. The quantum measurement paradoxes reveal deep tensions between different aspects of quantum mechanics. The deterministic Schrödinger equation that governs quantum evolution conflicts with the random, irreversible collapse postulate needed to explain measurement outcomes. The linear superposition principle that enables quantum interference seems incompatible with the nonlinear collapse process that creates definite observations. Attempts to resolve measurement paradoxes have led to increasingly exotic interpretations of quantum mechanics. The consciousness-based interpretation proposes that conscious observation plays a fundamental role in wave function collapse. Objective collapse theories suggest that wave functions spontaneously collapse due to gravitational or other physical effects. Pilot wave theories propose that particles have definite trajectories guided by quantum wave functions, eliminating the need for measurement collapse. Environmental decoherence provides a partial resolution by explaining how quantum superposition becomes practically unobservable without invoking fundamental collapse. According to decoherence theory, interactions with environmental degrees of freedom create entanglement that effectively destroys coherent superposition, making systems appear classical even though they remain technically quantum. However, decoherence doesn't fully solve the measurement problem because it doesn't explain why particular outcomes are observed. The practical implications of measurement paradoxes extend beyond theoretical physics to quantum technology development. Quantum computers must maintain coherent superposition while performing measurements that extract computational results without destroying quantum information. Understanding the boundaries between quantum and classical behavior is crucial for building reliable quantum devices that exploit quantum advantages while interfacing with classical control systems. Quantum foundational experiments continue to test the limits of measurement paradoxes. Using increasingly sophisticated techniques, recent experiments have created quantum time machines that allow quantum systems to interact with their own past states, testing whether quantum mechanics permits closed time-like curves. Others explore whether macroscopic objects can exhibit quantum behavior, pushing the boundaries where measurement paradoxes become experimentally accessible. The study of measurement paradoxes also reveals connections between quantum mechanics and fundamental questions about logic, mathematics, and the nature of physical law. Some researchers propose that quantum mechanics might require new logical frameworks that permit contradictory statements to be simultaneously true. Others suggest that measurement paradoxes reveal limitations of classical concepts like objectivity and reality that must be abandoned for a complete understanding of nature. What measurement paradoxes reveal about quantum mechanics extends far beyond technical physics to fundamental questions about the relationship between mind, measurement, and reality. These paradoxes demonstrate that quantum mechanics doesn't just describe unusual physics, it challenges the conceptual frameworks we use to understand existence itself. Understanding these paradoxes prepares us to explore how different interpretations of quantum mechanics propose radically different pictures of reality. Quantum interpretations. For nearly a century, physicists have agreed on the mathematical formalism of quantum mechanics while engaging in passionate debates about what it all means. The equations predict experimental results with stunning precision, but they offer multiple, contradictory explanations for why quantum particles behave when observed. These competing interpretations don't just represent different ways of thinking about the same physics, they propose fundamentally different pictures of reality that challenge everything from the nature of consciousness to the structure of the universe itself. The Copenhagen interpretation, developed primarily by Niels Bohr and Werner Heisenberg in the 1920s, became the orthodox view taught in most physics courses. According to this interpretation, quantum systems exist in superposition states described by wave functions until measurement causes instantaneous, random collapse into definite classical states. The Copenhagen interpretation treats the wave function as a complete description of quantum systems, with measurements serving as the fundamental boundary between quantum and classical worlds. But the Copenhagen interpretation raises as many questions as it answers. What exactly constitutes a measurement? How does the wave function know when to collapse? Why does collapse produce random outcomes when the Schrödinger equation is perfectly deterministic? Bohr argued that these questions were meaningless because quantum mechanics only describes measurement outcomes, not underlying reality. Yet this instrumentalist approach left many physicists unsatisfied with its apparent incompleteness. Hugh Everett III proposed a radically different solution in 1957. What if wave functions never collapse at all? His many worlds interpretation suggests that all possible measurement outcomes occur simultaneously in parallel branches of reality. When you measure an electron spin, the universe splits into separate branches where you observe each possible outcome. From your perspective in any particular branch, the measurement appears to have a definite result, but all outcomes are equally real in the complete quantum multiverse. The many worlds interpretation eliminates measurement paradoxes by proposing that everything, including observers, obeys quantum mechanics without exception. Schrödinger's cat exists in both alive and dead states in parallel branches of reality. When you open the box, you split into multiple versions of yourself, each observing one outcome while remaining unaware of your copies in other branches. This interpretation preserves quantum unitarity at the cost of postulating an infinity of parallel realities. But many worlds raises its own puzzles. How do branches split? And what determines the relative probabilities of different outcomes, if all possibilities are equally real? Why do we experience one particular sequence of events rather than others? The interpretation also faces the measure problem determining how to assign probabilities to outcomes when all possibilities occur in some branch of the multiverse. Hidden variable theories attempt to restore classical realism by proposing that quantum systems have definite properties even when unobserved. David Bohm developed the most sophisticated hidden variable interpretation, where particles have definite positions and velocities guided by quantum wave functions. In Bohmian mechanics, particles follow deterministic trajectories through space. But these trajectories depend on the wave function in highly non-local ways that reproduce quantum mechanical prediction. Bohmian mechanics eliminates measurement paradoxes by treating wave function collapse as an illusion arising from our incomplete knowledge of hidden variables. Particles always have definite properties. But these properties can depend on the complete experimental configuration in ways that create apparent randomness and non-locality, while Bohmian mechanics reproduces all quantum predictions. It requires faster-than-light influences between distant particles to maintain consistency. The consciousness-based interpretation, associated with physicists like Eugene Wigner and Henry Stepp, proposes that consciousness plays a fundamental role in wave function collapse. According to this view, quantum superposition persists until conscious observation creates definite reality through an irreducible mind-matter interaction. This interpretation takes seriously the apparent connection between measurement and awareness suggested by quantum measurement theory. But consciousness-based interpretations face significant challenges. How exactly does consciousness cause wave function collapse? Do all conscious beings collapse wave functions, or only humans? What about animals, computers, or hypothetical alien intelligences? The interpretation also struggles with modern neuroscience, which suggests that consciousness emerges from quantum and classical physical processes in brains, rather than being a fundamental feature that influences physics. Objective collapse theories propose that wave function collapse occurs spontaneously due to fundamental physical processes rather than measurement or consciousness. G or W theory, developed by Gherardi, Rimini, and Weber, suggests that wave functions spontaneously collapse at random intervals determined by the number of particles involved. These spontaneous collapses are rare for individual particles but become frequent for macroscopic objects, explaining why large systems appear classical. Roger Penrose has proposed that gravitational effects might trigger wave function collapse when superposition states create significant spacetime curvature. His orchestrated objective reduction or CHOR theory suggests that consciousness emerges from quantum processes in brain microtubules that avoid decoherence long enough for gravitational collapse to occur. While speculative, these theories attempt to solve the measurement problem through additional fundamental physics. Environmental decoherence provides a pragmatic approach that explains the emergence of classical behavior without invoking fundamental wave function collapse. According to decoherence theory, quantum systems become entangled with environmental degrees of freedom so rapidly that coherent superposition becomes practically unobservable. Environmental interaction creates the appearance of collapse while maintaining quantum unitarity throughout the universe. Decoherence successfully explains many features of the quantum classical transition, including why interference effects disappear when quantum systems interact with their environments. However, it doesn't fully solve the measurement problem because it doesn't explain why particular measurement outcomes are observed rather than others. Decoherence makes superposition unobservable, but doesn't eliminate it. The cubism quantum Bayesianism interpretation treats quantum states as subjective degrees of belief rather than objective properties of physical systems. According to QBISTs like Christopher Fuchs, wave functions represent an observer's personal betting odds for measurement outcomes rather than describing reality itself. This interpretation eliminates measurement paradoxes by treating quantum Mechanics as a theory about information and belief rather than objective physical processes. Cubism avoids many interpretational problems by being explicitly subjective, but it raises questions about scientific objectivity and the nature of physical law. If quantum states are personal beliefs, how can quantum mechanics be an objective theory of nature? How do different observers coordinate their beliefs to make successful predictions about shared experiments? Recent developments have produced even more exotic interpretations. The consistent histories approach attempts to assign probabilities to sequences of quantum events without invoking wave function collapse. Relational quantum mechanics suggests that quantum properties exist only relative to particular observers rather than absolutely. Some interpretations based on information theory propose that quantum mechanics emerges from fundamental constraints on information processing. The interpretation debate has practical implications for quantum technology development. Many worlds enthusiasts argue that quantum computers exploit parallel computation across multiple branches of reality. Bohmian mechanics proponents develop quantum trajectory methods for analyzing quantum systems. Decoherence theorists focus on controlling environmental interaction to maintain quantum coherence. Experimental tests attempting to distinguish between interpretations have produced intriguing but inconclusive results. Tests of consciousness-based collapse theories have found no evidence for consciousness affecting quantum measurements. Experiments exploring the classical quantum boundary continue pushing toward larger and more complex superposition states. Some researchers are developing tests that might distinguish between different interpretations through subtle predictions about measurement statistics. The interpretation debate also connects quantum mechanics to fundamental questions in philosophy of science. Do scientific theories describe objective reality? Or do they simply organize our observations? What constitutes an adequate explanation in physics? How should we understand theories that make identical empirical predictions but propose radically different ontologies? Modern approaches to quantum foundations increasingly emphasize information-theoretic principles rather than specific interpretations. Some researchers focus on deriving quantum mechanics from fundamental constraints on information processing, probabilistic reasoning, or correlational structures. These approaches attempt to understand why quantum mechanics has its particular mathematical form rather than debating the meaning of existing formalism. The study of quantum interpretations reveals how scientific theories can be empirically successful while remaining conceptually incomplete. Quantum mechanics works extraordinarily well for making predictions and developing technologies. But it leaves fundamental questions about the nature of reality unresolved. Different interpretations highlight different aspects of quantum phenomena while struggling to provide complete, consistent pictures of quantum reality. What the interpretation debate reveals extends beyond physics to fundamental questions about knowledge, reality, and the relationship between mathematics and nature. These different pictures of quantum reality prepare us to explore how our growing understanding of quantum observation is being harnessed for revolutionary technological applications that exploit the strange behavior of observed quantum systems. Quantum computing. Imagine a computer that could solve problems by exploring all possible solutions simultaneously, checking billions of potential answers in parallel before instantly identifying the correct one. This isn't science fiction, it's the fundamental operating principle of quantum computers. Machines that harness the strange behavior of observed quantum systems to perform calculations impossible for a classical computer. These devices exploit quantum superposition, entanglement, and measurement to tackle computational challenges that would take conventional computers longer than the age of the universe to solve. The power of quantum computing emerges from quantum bits, or qubits, that can exist in superposition of both 0 and 1 states simultaneously. While classical computers process information using bits that are definitively either 0 or 1, quantum computers manipulate qubits that can be in any combination of both states until measurement forces them to collapse into definite values. A quantum computer with just 300 qubits could exist in more superposition states than there are atoms in the observable universe. But quantum computing involves far more than simply scaling up the number of qubits. The real power comes from quantum entanglement, which allows qubits to share correlations that have no classical analog. Entangled qubits form collective quantum states where measuring one qubit instantly affects the measurement outcomes of all the others, creating computational resources that grow exponentially with the number of qubits rather than linearly as in classical systems. Consider how quantum algorithms exploit these quantum mechanical principles. Shor's algorithm, developed by mathematician Peter Shor in 1994, can factor large integers exponentially faster than any known classical method. The algorithm works by creating quantum superposition states that encode all possible factors simultaneously, then using quantum interference to amplify the probability of measuring the correct answer while canceling out wrong answers. This quantum speedup threatens current cryptographic systems that rely on the difficulty of factoring large numbers. Grover's search algorithm demonstrates another type of quantum advantage for searching in sorted databases. While classical computers must check each database entry individually, requiring on average half the total entries to find a target item, Grover's algorithm can find the target using only the square root of that number of operations. For a database with 1 million entries, classical search requires about 500,000 operations on average, while Grover's algorithm needs only about 1,000 quantum operations. The implementation of quantum computers requires extraordinary control over quantum systems while preserving the delicate superposition and entanglement states that enable quantum computation. Any unwanted interaction with the environment, thermal fluctuations, electromagnetic fields, even stray photons can destroy quantum coherence and cause computational errors. Current quantum computers operate at temperatures near absolute zero and are isolated in high vacuum chambers with extensive electromagnetic shielding. Different physical systems offer various approaches to building quantum computers. Superconducting quantum devices use electrical circuits that carry current in superposition states, creating artificial atoms that can be precisely controlled with microwave pulses. Ion trap computers use individual atoms suspended in electromagnetic fields, manipulating their quantum states with laser beams. Photonic quantum computers use individual photons as qubits, controlled through optical elements like beam splitters and phase shifters. Google's quantum supremacy demonstration in 2019 used a superconducting quantum processor called Sycamore to perform a specific calculation that would take classical computers thousands of years to complete. The calculation itself, sampling random quantum circuits, was specially designed to showcase quantum advantages rather than solve practical problems, but the demonstration proved that quantum computers can solve certain problems exponentially faster than classical machines. IBM's quantum computing efforts focus on building increasingly powerful quantum processors while developing quantum algorithms for practical applications. Their quantum computers are accessible through cloud services that allow researchers worldwide to run quantum programs and explore quantum algorithms. IBM's roadmap includes plans for quantum computers with thousands of qubits that could solve real-world optimization, chemistry, and machine learning problems. The development of quantum error correction represents one of the greatest challenges in quantum computing. Quantum states are extraordinarily fragile, and current quantum computers experience error rates millions of times higher than classical computers. Quantum error correction uses entanglement to distribute quantum information across multiple physical qubits, enabling detection and correction of errors without destroying the quantum information being processed. Surface code error correction, developed by researchers including Austin Fowler and John Preskill, provides the most promising approach for large-scale quantum computing. Surface codes can correct both bit flip and phase flip errors using only nearest neighbor interactions between qubits, making them practical to implement with current quantum technologies. However, surface codes require hundreds or thousands of physical qubits to create each logical qubit with sufficient error correction. Quantum algorithms continue to be developed for specific applications where quantum computers might provide significant advantages. Quantum chemistry algorithms can simulate molecular systems that are intractable for classical computers, potentially revolutionizing drug discovery and materials science. Quantum optimization algorithms could solve logistics problems, financial modeling, and machine learning challenges that exceed classical computational capabilities. The near-term applications of quantum computing focus on problems where quantum computers might provide advantages even without full error correction. These noisy intermediate-scale quantum NISQ algorithms are designed to be robust against the errors present in current quantum devices. Variational quantum algorithms use classical computers to optimize quantum circuits for specific problems, combining quantum and classical computation in hybrid approaches. Quantum machine learning explores how quantum computers might enhance artificial intelligence and pattern recognition. Quantum neural networks could potentially process information in ways impossible for classical systems. Though the practical advantages remain unclear, some quantum machine learning algorithms promise exponential speedups for certain data analysis tasks, while others focus on quantum data that has no classical analog. The implications of practical quantum computing extend far beyond faster calculations. Current internet security relies on cryptographic systems that would be broken by large-scale quantum computers, Ning Shor's algorithm. This has prompted development of post-quantum cryptography encryption methods that remain secure even against quantum attacks. The transition to quantum-resistant cryptography is becoming urgent as quantum computers become more powerful. Quantum communication networks could use quantum computers as nodes in quantum internet systems that enable perfectly secure communication through quantum key distribution and quantum teleportation. These quantum networks would allow distributed quantum computing where quantum algorithms run across multiple quantum computers connected by quantum communication links. The philosophical implications of quantum computing challenge our understanding of computation and information processing. If quantum computers can solve problems by exploring all possible solutions simultaneously, what does this suggest about the nature of mathematical truth and computational complexity? Some interpretations propose that quantum computers access parallel universes to perform their calculations, while others suggest that quantum computation reveals deep connections between information and physical reality. The development of quantum programming languages and software tools is enabling more researchers to explore quantum algorithms without requiring deep knowledge of quantum physics. Languages like Qiskit, Cirq, and QHash allow programmers to write quantum algorithms using familiar programming constructs while abstracting away the underlying quantum mechanics. These tools are democratizing access to quantum computing and accelerating algorithm development. Commercial applications of quantum computing are beginning to emerge in optimization, simulation, and machine learning. Companies like D-Wave offer quantum annealers specialized for optimization problems, while other firms develop software for running quantum algorithms on current quantum hardware. Quantum computing industry is attracting billions of dollars in investment as companies race to achieve practical quantum advantages. The competition between different quantum computing approaches, superconducting circuits, trapped ions, photonics, topological qubits, and others continues to drive rapid progress in quantum hardware. Each approach has different advantages for scaling, error rates, and types of quantum operations. And it remains unclear which technologies will ultimately prove most practical for large-scale quantum computing. What quantum computing reveals about harnessing quantum behavior through careful observation and control demonstrates how our understanding of quantum measurement can be transformed into revolutionary computational capabilities. The precise manipulation of quantum superposition and entanglement required for quantum computing represents a triumph of quantum control that connects fundamental physics to practical technology. This mastery of quantum behavior prepares us to explore other applications where quantum measurement principles enable unprecedented technological capabilities.